Okay, in Part D, we're asked to use the series that we found in Part C, which I've shown here, to find a rational number a such that absolute value of a minus natural log of 5 over 4 has got to be less than 100 and justify your answer. So at first sight, this might make no sense, but we'll go step by step through it. The first thing is that when we see something like absolute value a minus ln of 5/4 less than 100, we know that we're talking about the error, or we're talking about the remainder. And since we're working with ln of 1 plus x squared, well, this is going to be our actual here, and this a may stand for approximate. We'll call it estimate right now, and that's our estimate, or our approximate value that we get by using the Taylor series that we have here. So hopefully you've seen this form before. We have the estimate, the difference between the estimate and the actual. An absolute value of that has to be less than a certain amount. All right, so since we're working with a Taylor series here, not just a Taylor series, we have an alternating series. This is an alternating series where terms decrease in absolute value to 0, so we can use the alternating series remainder theorem, which says the error will be less than the first excluded term. Alright, so that's what we're going to be working with here. And now, a couple of things that we need to pay attention to here. The function that we have is ln of 1 plus x squared, and the actual value that we're using in the problem is ln of 5/4. So you really need to find out the value of x that we're using here. So we have 1 plus x squared then has to equal 5/4. We subtract 1 from both sides and we get x squared is 1/4. Now x would be plus or minus 1/2. And we'll just use the positive value right now. I can't off the top of my head tell if there's a reason why the negative is not valid in this case, but let's work with the positive. So what that means then is that we're working with x equals 1/2. And when we work with x equals 1/2, we'll have 1/2 squared minus 1/2 to the 4th over 2 plus 1/2 to the 6th over 3 minus 1/2 to the 8th over 4, etc. Let's see what that looks like. That's going to be 1/4. 2 to the 4th is 16. Then that's going to be minus 1 over 32. Then 2 to the 6th power is 64. 64 times 3 is 1 over 192 would be the next term. And 2 to the 8th is 256 times 4 is 1024. So that would be 1 over 1024. So when x is 1/2, our Taylor series that we've made will play out in this way: 1/4 minus 1/32, etc. And what we're really looking for here is how many terms do we need so that our error will be less than 100? Well, since the error is made up of the first excluded term, we're just looking for the first term that is less than 1/100th. And that happens to be the third term here. So what that means is then we just need to use the first two terms, and that's going to be our value for a. So let's see if we work this out. We would need to multiply here top and bottom by 8. So we'd get 8 30-seconds minus 1 30-second is equal to 7 30-seconds. So what that means is that if we used a second, that's not second degree, this is using the fourth degree Taylor polynomial evaluated at 1/2, we subtracted that from the actual value that we're trying to represent there, which is ln of 5/4, that the absolute value of that difference must come up to be less than 1/100th, sorry. And so that a, which is our t sub 4 of 1/2, is just 7 30-seconds. And that's what would happen here. Now, if we wanted to give this a try on the graphing calculator, which by the way you don't have access to in doing this particular problem, but if we wanted to show a point here, and that would say that 7 30-seconds, then minus natural log of 5 divided by 4, and we won't pay attention to the sign since we're interested in the absolute value, is going to be negative 0.004, which is less than 0.01, which is 1/100th. So all we needed to do was use the first two terms of that Taylor series evaluated at 1/2 in order to get an error that was less than 1/100th. And hopefully this is clear. I'll leave a copy of that screen in the on the printout, and that'll do it for this problem.